All right. So welcome everyone to the Topological Complexity seminar of the Applied Algebraic Topology Research Network. And today I'm delighted to introduce the speaker for this session, Yuki Minowa from Kyoto University, who will speak to us on the rational sequential parametrized version of Farber's topological complexity. So Yuki, please take it away.
Thank you. Uh, my name is Yuki Minowa, and I am the PhD student in Kyoto University. Before I start talking, I would like to thank organizers for inviting me as a speaker of this seminar. Today, I will talk about the rational homotopy theoretic viewpoint of the sequential parametrized topological complexity, which is a variant of the topological complexity. So let's begin with the section 1. In this section, we recall the concept of robot motion planning and topological complexity and recall some variants of it. So to start with, what is a robot motion planning? So let X be the configuration space of robots in a space. So then robot motion planning is a program that takes a pair of configurations A and B as an input and provides a path in X from A to B as an output. This can be formulated as follows. Then a robot motion planning is a section, but not necessarily continuous section of the following fibration pi. So the fibration pi is from the path space Px to x times x and maps path gamma to the tuple of the initial and terminal point. So as we can easily see that for a space X, there exists a continuous robot motion planning if and only if X is contractible. So the topological complexity is a quantity to measure the degree of instability, or in other words, the discontinuity of a robot motion planning in a space. So let's see the precise definition of the topological complexity. The topological complexity of a space X, which is denoted by Tcx, is the minimal integer k such that x times x is covered by k plus 1 open sets having local section of the fibration pi, which we have seen above. So now remark that our definition of the topological complexity is somehow normalized. In other words, starting with 0. So for space X, Tcx is equal to 0 if and only if it is contractible. So let us briefly see some examples of the topological complexity of certain spaces. For n sphere, there is an identity that TCSN is equal to 1 when n is odd and 2 when n is even. Another example is the configuration space. Let us denote FYM by the configuration space of m points in a space Y. Then Farber and Oprea computed the topological complexity of the configuration space m-point configuration space in a space Rd, and it is computed as 2m-2 when d is odd and 2m-3 when d is even. So along with the computation of the topological complexity for certain spaces, there have been many studies on a variation of a motion planning problem and corresponding homotopy invariants. So here's some list, not all, of the variants of topological complexity. In this talk, we focus on the second and the last one, so namely the sequential topological complexity and parametrized topological complexity. Sequential topological complexity was introduced by Rudiak, and it considers a higher robot motion planning. So as an input of the program, not only the initial and terminal point, but some intermediate point are given, and it can be described as a section of the fibration pi r, which is from the path space to the r's copy of x, and maps some path to the intermediate r points. So the second one, parametrized topological complexity, was introduced by Cohen and Farber and Weinberger, and it formulates the robot motion planning problem, which involves external constraints as parameters. So these constraints are represented as the fibration. So these two concepts are combined by Farber and Paul, and our main topic, sequential parametrized topological complexity, is defined. Let P from X to B be a fibration with a path-connected fiber. Let XRB denote the fiber-wise product of R copies of X over B, and let PBX denote the subspace of a path space, which consists of the path gamma such that after composing the projection P, it becomes a constant path. So the formal definition of the sequential parameterized topological complexity is that for R being equal to 2 or greater than 2, the Rth sequential parameterized topological complexity of a fibration P from X to B is the minimal integer k, such that XRB is covered by k plus 1 open sets, which have local sections of the evaluation fibration of pi r from PBX to XRB. So this fibration maps path space gamma to the intermediate R points, including initial points and terminal points. So let us see some examples of the sequential parameterized topological complexity. So the easiest case is the trivial fibration, that is, if X is the product of the fiber and base, so then the motion planning problem on F can be extended to all the total space X, and then we will obtain that TCR from X to B is equal to TCRF. So other case is the Fadel-Neuhaus fibration, which is from the FRDM plus N to FRDM, and it is a projection of the first endpoints in a configuration space. This fibration formulates the certain kinds of the motion planning problem such that there is a n robots and m obstacles in the space Rd, and the obstacles are fixed and blocks the motion of robots. Then, in this situation, the topological R's sequential parameterized topological complexity of this fibration is completely determined by Farber and Paul, and it is also depending on whether D is odd or even. So now we have recalled the topological complexity, and today's topic, sequential parametrized topological complexity. So the second, now we will proceed to the section 2, rational model. Uh, so our today's topic is the rational homotopy theoretic aspect of the topological complexity of sequential parameterized topological complexity. So we will see, we will establish an algebraic model of the sequential parameterized topological complexity, which is due to the Karskel-Vera. So let's see. Uh, First, we recall the definition of the sectional category, and this is a sectional category of a map F from X to By, which is denoted by sectional category F, is the minimal category minimal integer k, such that Y is covered by k plus 1 open sets having local homotopy section of F. So, by definition, the R's sequential parameterized topological complexity of a fibration X to B is equal to the sectional category of the evaluation fibration pi R from PBX to XRB. Then, since pi R is equivalent to the fiber-wise diagonal map, delta R from X to XRB, which maps a point in X to the or the same point in XRB. So since the sectional category is a fiber-wise homotopy invariant, we get that TCR X to B is equal to the sectional category of the delta R. Uh, in what follows, we accept this definition or this equation of the topological as a topological complexity of X to B. So we will see an algebraic description of rational sectional category. So we mentioned that in what follows we only consider rational spaces which are path-connected, nilpotent, and of finite rational types unless otherwise specified. This is in fact not necessary, and we only consider some kinds of simply connected spaces instead of nilpotent one. So let F from X to Y be a map of rational spaces which admits a homotopy retraction R from Y to X. Then F has a model phi, a CDGA model phi from A tensor lambda W to A, which is a retraction of a relative Sullivan algebra A to A tensor lambda W, which models map R. Then Karskel-Vera studied the rational sectional category and obtained the following theorem. The sectional category of F is equal to the minimal integer k, such that the CDGA projection rho k from A tensor lambda W to A tensor lambda W over kernel phi or to the k plus 1 admits a homotopy retraction. This is a generalization of the description of the rational LS category, which is due to Felix and Halperin. So we are now ready to apply this theorem to our sequential parametrized topological complexity. Let F to X to B be a rational fibration with a relative Sullivan model C to C tensor lambda V to lambda V. Then delta R from X to XRB admits a retraction, which is the first projection P1, and thus has a surjective model, which is described as the tensor product of identity and R's multiplication. Then, by the theorem above, we get the following proposition. The R's sequential parametrized topological complexity TCR x2b is the minimal integer k such that the CDGA projection rho k from C tensor lambda v tensor R to C tensor lambda v tensor R over kernel identity tensor lambda R to the k plus 1 admits a homotopy retraction. As we can see, this is completely algebraic description. However, it is very difficult to determine the actual value of sequential parameterized topological complexity by this definition. So we still need some kinds of lower or upper bounds to evaluate the value of the sequential parameterized topological complexity.
So Yuki, can I ask
hi,
a question?
okay.
In that proposition, this refers to the rational sequential parameterized topological complexity.
So rational sequential parameterized topological complexity.
Great. Okay. Thank you.
Thank you. So let's now we are ready to state our main result, which gives an upper bound of rational sequential parameterized topological complexity when the fibration admits a specific decomposition. So first, we introduce the concept of odd degree extension. So one of the features of rational LS category and rational topological complexity is that under some assumptions, which we will explain as the odd degree extension, they have very simple algebraic upper bounds and which are usually shaper than the other integral upper bounds. So we now say that a rational space X admits an odd degree extension if there is a rational space X hat and a map from X to X hat such that the kernel of the map pi X to pi X hat, which is a homotopy maps between two homotopy groups, is finite dimensional and concentrated in odd degrees. So for any even n, pi n, a kernel of pi n is 0. Then the map X to X hat has a minimal relative Sullivan model C to C tensor lambda V such that V is of finite dimension and concentrated in odd degrees. So let let M be the dimension of the kernel kernel of pi x to pi x hat as a vector space. So most simple case for M being 1, the map x to x hat is rationally considered as a rational fibration with a fiber being the Eilenberg-Maclaurin space K Q 2n plus 1 or the rational sphere of odd dimension. So Fakes and Halpern showed that there is a following inequality. So the category of rational space X is equal to or less than the category of X hat plus M. Hamoun the analog of this result in the TC is due to Hamoun and Rami and Vandembroucq, and it's given recently. And there is an in following inequality, TCX is equal to or less than TCX hat plus M. So this is very simple result, and this is very also very strong upper bound. So our aim of this talk is to generalize the results of these two results, especially by the Hamoun, Rami, and Vandembroucq, and give an algebraic upper bound of TCR x to b in terms of an so-called odd degree extension. Uh, so we extend the definition of the odd degree extension to rational fibrations. So a rational fibration f to x to b is said to admit an odd degree extension if there is a following homotopy commutative diagram fx to b to f hat x hat to b such that the bottom row f hat to x hat to b is a rational fibration and f is an odd degree extension of f hat. So this is also considered as some kinds of extension by even dimensional sphere as odd dimensional sphere as we have been before. So now we state the first main theorem. Let f to x to b be a fibration of rational nilpotent spaces of rational finite type, which is an odd degree extension of f hat to x hat to b. Then, if we denote the kernel of pi f to pi f hat uh, by of the dimension m, then the sequential parametrized topological complexity TCR x to b is equal to or less than TCR x hat to b plus m times r minus 1. So the proof is the idea of a proof is basically based on that is by in the case of an odd degree extension of TC. So by the induction of the generator of the Sullivan algebra of the fiber, which is concentrated in odd degrees, and differs at most one is we can see that when there is only one generator, the two parameterized rational sequential parameterized topological complexity differs at most one, and then going by induction, this result can be obtained. So in particular, we can determine TCR x to b if f hat is contractible, that is, f is concentrated in odd degrees. So let f to x to b be a fibration of rational nilpotent spaces of finite rational type. Suppose that f is elliptic and concentrated in odd degrees. Then we have the following equation. So TCR x to b is equal to the TCR of a fiber f, and which is equal to r minus 1 times dimension of the pi odd f. So to prove this theorem, an upper bound is given by the above theorem, and the lower bound is the first equation of the lower bound is given by the definition, and the second one is somehow due to an argument of Hess or recently Kishimoto and Yamaguchi. And then the value of lower bound and upper bound coincides, and we get this identity. So before concluding this section, we remark something. We have some remarks. One is the second theorem, which we have seen, can be related to these previously known results on the parameterized topological complexity. The first result is on the principal bundle or principal bundle x to b, a principal G bundle where G is a connected topological group. In this situation, the R sequential parameterized topological complexity TCR from x to b is equal to the R's sequential topological complexity of G, and which is equal to the category of G to the R minus 1. So this result, the second theorem corresponds to this result because the finite type topological group, its rational model is finite of if G is a finite rational type, then its Sullivan model has only odd degree generator and has a trivial differentials. So the next result rewriting the second theorem is due to my previous work. And this theorem, this result is a generalization on the estimation of the parameterized topological complexity of sphere bundles. So so let S to n plus 1 to x to sigma b is a suspension of b, be a homotopy fibration with b connected. Then there is a following inequality such that Tc2 of x to suspension b is equal to or less than 2. So I utilize this result to determine some kinds of the parameterized topological complexity of the spherical fibration over spheres. We also remarked that the parameterized topological complexity of some fibration and the parameterized topological complexity of its rationalization may differ. So, in fact, let S for n minus 1 to t to S for n be denote the unit tangent bundle of a sphere S for n. Then we have seen that its rationalization tq to S for nq, its parameterized topological complexity is 1 as the fiber is the rational odd-dimensional sphere. Whereas I proved that the Tc2 of t to S for n integral result is in fact 2. This result is not coming from the computation of the cohomology, but rather the concept of weak sectional category and computing some kinds of four-cell complex, the weak category of four-cell complex, and it is somehow related to the two torsion of the homotopy groups, and it's vanished after rationalization. So now we proceed to the section 4. And in section 4, we introduce a formal power series, which is a generalization of the TC generating function, which is introduced by Farber and Oprea. So let us see the TC generating function. So we TC generating function is a formal power series which has the coefficient of the sequential topological complexity. It describes the growth of the sequential topological complexity of a certain space. So this can be easily generalized to the sequential parametrized topological complexity. For a fibration P from X to B, Farber and Paul consider the formal power series FPZ, uh, uh, which with the coefficient of ZR being TCR plus 1 from X to B. So naturally we can ask the following question. So for what fibration f to x to b of finite rational type is fpz a rational function pz over 1 minus z to 2 to the 2 such that pz is a polynomial with p1 is equal to scat f. So to answer, we will give two affirmative cases for this question. So the first case is from the second theorem, and so namely when the fiber f is concentrated on odd degrees. So let f to x to b be a rational fibration of finite rational type such that f is elliptic and concentrated in odd degrees. Then, as the topological R sequential parameterized topological complexity is, as we have seen, grown by scat f. So fpz is equal to scat f over 1 minus z squared. So we have also another affirmative cases in which TCR x to b equals to the so-called zero divisors couplings ZCLR from x to b, which is the generalization of the zero divisors couplings of the topological complexity and defined analogously by the uh, nilpotency of the kernel of the kernel of the induced map or induced cohomology map of the fiberwise diagonal map. And so is computed. So the TCR x to b is in this case, in the following cases, can be computed homologically. So let f being S2nq or a CPnq. So this is a rationalization of the even dimensional sphere or a complex projective manifold. And let f to x to b a rational fibration such that b is formal. Then we can prove that the fibration, these kinds of fibration, all supports the above question. So this theorem is somehow a special case of so-called the Halpern conjecture, one of the unsolved problem in the rational homotopy theory. So now we proceed to the last section, section 5. So we exhibit some further problems that may enhance the study of the rational sequential parameterized topological complexity. The first problem is regarding the TC generating functions. So the above theorem, above proposition on the TC generating function comes from this theorem. So let f to x to b be a rational fibration which is totally non-cohomologous to 0. If f is elliptic and formal space and b is formal, then the R's sequential topological complexity of x to b is equal to the homological quantity, the so-called zero divisors cup ranks of x to b. This is analogous to the argument that the topological complexity of a space X is equal to its zero cups length if X is a formal. So in this case, the first question is for any rational fibration f to x to be above. So that is the sequential topological complexity equals to the zero divisors cup length is fpx, fpz a rational function pz over 1 minus z squared such that pz is a polynomial with p1 is equal to cat f or not. So why this is a problem is that the lower bound evaluation has no problem, but on the upper bound, on the other hand, when it comes to the upper bound evaluation, this is somehow very difficult as this contains no odd degree extension and very they are very rough. Currently, there exist very rough upper bound estimations. So the second problem is regarding to the algebraic description of the sequential parametrized topological complexity. Let recall that rho k CDG projection rho k in the algebraic description of TCR x to b. So we have defined that TCR x to b as a minimal integer k such that this CDGA projection admits so homotopy retraction as a CDGA. So along with the as an analog of the definition of the module topological complexity or some kind of module category, we can define the module R's sequential parameterized topological complexity of x to b as the minimal integer k such that rho k admits a differential C tensor lambda v tensor R module homotopy retraction. So in the LS categories case, under some assumption, module cat is equal to the cat itself. But how about the topological complexity, or more generally, the rational module R's sequential parameterized topological complexity? So the question is, for any rational fibration, x to b is the module sequential parameterized topological complexity is equal to the its sequential parameterized topological complexity or not. This problem, I think this problem is very crucial and even connected to the first problem, first question, as in the way of study of Kesselring Hess, and the evaluation of the difference of the module TC growth of the module topological complexity or module sequential parameterized topological complexity is rather easy. So we have the some kinds of the zero cups kinds of the cup lengths of f is a good lower bound of that, and recently Hamoun proved that in the suitable situation, category F is actually the lower bound. So if this question is true, this question is true, the first problem may be solved easily, and if this is not true, then the fibration can be maybe a counter example to the first question. But these two problems seems a bit challenging for, but I think it was trying to study these follow these questions. So that is all for my presentation. Thank you for your attention.
Well, please, everyone, join me to thank the speaker for a great presentation. So if anyone has any questions, please just unmute yourselves.
I have a question. I may have missed. Can you hear me?
Yes.
Okay, I can hear you.
Yeah, thank you very much for a nice talk. I may have missed something, but did you say anything about the formal case? So if the fiber is formal, can you anything?
Thank you. And I now really actually I haven't mentioned formal cases in this talk. But on my recent paper, I prove maybe this theorem now this first theorem is due to my is on my paper recent paper, and this is some kinds of formal cases. So F and B requires to be formal space, and further the space F is required to elliptic, and the total fibration is required to totally non-cohomologous to 0. And in this situation, the space X becomes also formal, and 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 somehow the fiber-wise diagonal map from X to XRB becomes also a formal map. So then this equation falls.
Okay, thanks. So formality of the map is what's needed. Yeah. Okay.
Yeah, and I think if I say additionally, this is very essential. These are some kinds of these assumptions very essential. And for example, if F is elliptic and formal and B is formal, but it's not totally non-homologous to 0, then there is some fibration that the zero divisors cup length is less than the TCR. So these two does not coincide. So other condition such that F is elliptic or F is formal or B is formal is also essential. Cannot be omitted.
Interesting. Thanks.
Thank you for your question.
And Yuki, you mentioned it briefly, but those assumptions are tied up with the Halperin conjecture, right? That if F is elliptic and it has 0 homotopy Euler characteristic, then you should have a totally non-cohomologous to 0 fibration.
Yes. Sorry. Maybe I missed something. Or so as you mentioned, this is a very crucial problem, and this is the deeply connected to the the Halperin conjecture I mentioned. And in this situation, the totally non-homologousness is equivalent to the some kinds of pureness of vibration, and the Halperin conjecture says that if F is elliptic and formal, if F is elliptic formal or some kinds of so-called F0 space, then all the fibration is totally non-cohomologous to 0, and which is still open. And we are only considering the affirmative case in other. To say we are only considering the affirmative cases of the Halpern conjecture. Is that okay? Or
Yes, yeah.
Well, I have another question. So at the end of the third section of your talk, you gave us an example of a space for which the rational non-rational, that one. At the bottom, the rational and non-rational sequential, well, it's not sequential in this case, but it's a parametrized TC of a space may differ. So I was wondering if you can see this behavior in the case of the Fadel-Neuwirth fibrations, where you see a difference in dimensions.
So Farber-Neuwirth in Farber, I think in the Farber-Neuwirth fibration case, the lower bound computation is enough for the homological. What to say? Rational homological evaluation is enough in these cases. Sorry, in Farber and Paul's cases. So maybe in these cases, rational one and the parameterized one I think they don't differ.
I would suppose so in the case of an odd-dimensional Euclidean space.
So that's that maybe I think you are. Now I understand. Maybe you're right. I think so. I have not computed it accurately, and so maybe I can do some computation, and it may differ or it may not. But I think it is very interesting question. I think.
Great, thank you.
Thank you.
All right. Well, if I'm going to stop the recording, and if people can just keep asking after this, if you want.